So we've just been talking about how when we consider a thin version of the number of accidents, so we want to model the number of claims paid by using a thin version of the number of accidents. Well, then basically what we do is we look at the number of accidents, and for each accident we ask, what's the probability that sounded weird. What's the probability that that accident results in a damage that is greater than the deductible? And if it turns out that it is greater than the deductible, then that means that this I is 1. And if it's smaller than the deductible, then this I is 0. So what we want to do now is we want to take a look at how the formula in the book comes into play. So in the book, we have a formula on the thin version of a stochastic variable, and that looks something like, let's see. So they say, let n be given as the sum of IID Bernoulli variables up to n star. So we have n star accidents, and for each of them we ask, is this accident greater than the deductible? Yes or no. Is this greater than the deductible? Yes or no, yes or no, yes or no, yes or no, and so on. So the number of yeses that are counted out of the n star accidents are then the number of paid claims. What they say in the book now is that the probability that the thinned n takes the value k is given as, and then I'll just leave some space here. So in the book they say it's the sum for n going from k up to infinity of the condition probability that n is equal to k, given that n star is equal to n multiplied by the probability that n star is in fact equal to n, and that is again equal to the sum where we substitute in the point probability for a binomial distribution with parameters n and p, n and q, sorry. 1 minus q, n minus k, probability of n star equals n. So what is meant by this in the book, and how should we understand this? Well, first of all, let's just think about, well, what should happen for n to be equal to k? Well, there are different cases where n is equal to k, right? Either n is equal to k and n star is equal to k as well. Can it be possible that n is equal to k, but n star, for example, is something smaller than k? Well, let's think about it. N can be at most n star, right? So n star cannot be smaller than n. And what we have then is that when n is equal to k, then the probability that n is equal to k and n star is equal to, for example, k minus 1, well, this probability is just 0 because it's impossible. We cannot have more accidents than we have accidents paid. No, sorry, we cannot have less accidents than we have accidents paid. So that is why the probability that n is equal to k is the same as the probability that n is equal to k, and that n star takes any value n that is greater than equal to k. So I can write it this way, or I can write it as n equal k up to infinity. So those are two different ways of attacking that. Now, so what we've written here basically is the probability that n is equal to k. So the probability that the number of paid claims is equal to k is given by the probability of the number of paid claims being equal to k and n star being equal to k, or n being k and n star being k plus 1, or n equal to k plus 2 and n star n equal k and n star being k plus 2. So the number of paid claims can become k in different ways, where those different ways consists of n star being k, or k plus 1, or k plus 2, or k plus 3. So that's how we go from here to here. Now, the way we go from here down to here is that we take a look at, well, what is this thing actually? It's a joint probability, right? It's a joint probability of n being equal to k and n star being equal to n. And what we know is the probability of the intersection of two events is equal to the probability of one event given the other multiplied by the probability of what we condition on. So again, we use this formula here and we get this thing. And in fact, it kind of makes sense. We look at each case where n can be equal to k. That is given n star is equal to k, or n star given is equal to k plus 1, and so on. And then we weight each case using the probability of that actually happening. So intuitively, it kind of makes sense. So what happens from here down to here? Well, the probability of n star being equal to n just stays, so nothing new under the sun there. However, this is pretty interesting. What are we looking at? Well, we're looking at the probability that n is equal to k, given that n star is equal to n. Now, the thing about n is it is defined as the sum of Bernoulli variables, of n star Bernoulli variables. So given that n star is equal to n, then little n, then n, the capital N, is equal to the sum of little n Bernoulli variables. And given that this is the case here, what is then the probability that this n attains exactly the value k? Well, that can happen if the first k ii's are equal to 1. It can also happen if the last k ii's are equal to 1. It can also happen if we have one ii that is equal to 1, and then some of them are equal to 0, and then the last k minus 1 ii's are equal to 1. So essentially, the probability that n is equal to k, given that the n star that decides what we sum up to is a certain number, well, that is just the number of different ways we can pick k ones out of n numbers. So that is exactly what we use the binomial distribution for. So what we have here is the binomial point probability in the value k, where we pull k out of n elements. So this is n choose k, which means the number of ways we can choose k elements out of n elements. And here we have the probability of choosing k elements and the probability of not choosing the last n minus k elements. So this is the binomial distribution's point probabilities, and now you also know why we actually use them. And this is the entire reason why the thin version has point probabilities that look like this. Now, in the exercise itself, we won't actually be using this formula. So haha, cheated you guys. We're actually only going to look at this part. And that is, of course, very nice. And the reason that we can do that is because, well, we have so few cases to look at. So in the next video, we will take a look at this exercise and do the calculations.